Okay, so welcome to the Kirk Public Lecture of the program on stochastic systems for anomalous diffusion. My name is Alex Mijatovic. I'm one of the organizers of this program, and it's my great pleasure to introduce Professor Ruth Williams, who will deliver this lecture for us today. So I thought, Ruth is, of course, very well known and really needs no introduction, but just to say a few words about the type of mathematics that she does. I mean, it's quite astonishing. It's really interdisciplinary and always is about developing rigorous mathematical tools and rigorous mathematical theories in order to sort of say something new about applications. Okay? So this led her to many, many breakthroughs in her career in various areas of mathematics, like, for example, the foundational theory that she developed on obliquely reflective Brownian motion in a wedge. Of course, many accolades and recognitions followed, maybe too many to list in an introduction like this. So instead of doing that, I will just invite Ruth to begin with her lecture. Please, thank you.
Well, thank you, Alex, for the kind invitation, kind introduction, and also to the organizers of the program on stochastic systems and anomalous diffusion for the invitation to speak here, and also to the Isaac Newton Institute and also the Turner Kirk Trust for sponsoring this lecture. So I'm going to, at a high level, what I'm going to be talking about are what I call stochastic processing networks. And this is kind of a cartoon of maybe a way to think about these initially. So these are networks that process things, that have processing resources in them, which could be servers or something that's able to process things, machines or something like that in an application. And entities come into this system that need processing at various nodes in the network, and they eventually leave. And depending on the application, the entities might be customers of different types, packets of data, maybe files being transmitted over the internet, or jobs, or in transportation, it could be vehicles going through a network of roadways. What's stochastic about these models, that way in which things arrive can be random. The amount of time it takes to process something at a node can be random, and even the movement within the network can be probabilistic or random. So this kind of stochastic processing network comes up in a variety of applications in science and engineering. I've just shown a few examples here. In, for example, semiconductor wafer fabrication, you have expensive machines that process wafers or chips. During the processing, the wafers might have to return to these machines multiple times from different stages of processing. So you can see already it's a quite complicated network, and trying to figure out how it behaves and what might cause bottlenecks is a challenging problem. But also, we're probably all familiar with customer service situations where we have, for example, in telephone call centers, agents who are often cross-trained, who answer telephone calls for example, a bank or other large types of services. In the internet, the processing resources you can think of as routers in the internet that route files or packets of data from their sources to the destination. Even in computing, you can think of central processing units as a processing resource that need to process jobs. In transportation, you can think of sections of roadway as being a resource, and of course the vehicles would be the entities that are even of different types that are processed through those networks. And even in synthetic biology, you can think of proteins of different types that compete for the attention of an enzymatic processor. So one thing about these networks is that often the capacity of the resources, the processing resources, is limited, which can lead to bottlenecks and queues. This is kind of an extreme example of people queuing to get into Monet's garden in Giverny in France. It's wonderful once you get inside, but of course often there's a queue that you need to wait in. And there's sort of one thing I want to say at the beginning is that with this queuing phenomenon, there's sort of two extreme regimes, which I'll call the underloaded and the overloaded regime. So the underloaded regime is exemplified by this picture of people really not queuing for iPad minis in 2012, where the average demand was less than the capacity. Queues were short. There might be some queuing for stochastic effects, and there's little competition for the processing or service. At the other extreme, the average demand is greater than the processing capacity. Queues tend to be long, and there's strong competition if there are different types of entities vying for the attention of a processor. Now, in between, there's kind of a sweet spot, which I'll call the balance point, or sometimes people call it, say that things are heavily loaded or in heavy traffic, where the average demand is roughly equal to the processing capacity. And this is a place where system managers like to position systems because it typically means that there's not much idleness in the system or not much unused capacity. So we're very interested in trying to understand the behavior of these stochastic processing networks in this regime. And the theme of my story is that reflective diffusions can help us to understand what's going on there. I'm mostly going to focus on analyzing systems, but of course, if you want to control these systems, you have to be able to analyze the performance of control. So this is also relevant to control of these kinds of networks. So since this is a public lecture, I'm going to start with a very simple example to illustrate the kinds of things we're talking about. Of course, there's a long history of queuing and stochastic networks and fundamental contributions there at Cambridge. So this is a little bit like bringing coals to Newcastle, but I have a theme here that I'm trying to illustrate. So a little bit like a random walk through these stochastic networks and the associated reflecting diffusion approximations. So this is a very simple setup here. We have a single processor or server and a queue where entities, let's call them jobs, just so I can use one generic name. Jobs come into the system, they queue up in the order in which they arrive, and then they're served in that order by the processor or server. So this is what's called first come, first served, or first in, first out service. So this is sort of a very simple network structure. And just as a thought experiment, suppose the server is very reliable, so that suppose it can process one job per minute exactly. So at the end of each minute, if there was a job to process, it'll be at the head of the line, it'll be processed and will depart the system. On the other hand, with the arrivals, let's first of all consider where the arrivals are also very predictable, and that one job arrives at the beginning of each minute. And for specificity, let's suppose that the service departure occurs first if there is one, and then the job arrives. So this is a balanced system. The average rate at which things are arriving is equal to the average rate at which they can be served. And everything is deterministic here. So in fact, no queue will build up. However, a little bit of randomness can make a difference. Here I'm going to make the arrivals random, but you could get similar effects if you make the service have some random fluctuations in it. So for a second scenario, let's keep the reliable server, but now at the beginning of each minute, either 0 jobs arrive or 2 jobs arrive, and they go into the queue. And those events happen with probability of half each. So it's equally likely that 0 jobs arrive or 2 jobs arrive. Then you can simulate this using coin flips, for example. And on an average, there'll still be 1 arrival per minute. But now there's some stochasticity to those arrivals. And I know some people are familiar with random walk. So if you actually watch what's happening in the queue and think about it, when there are things in the queue, each minute, suppose that at the beginning of the minute, 0 jobs arrive. Then the server will work on a job that's in the queue. And then at the end of the minute, the job will depart. So the net number of jobs in the queue at the end of the minute will decrease by 1. And that will happen with probably a half, because there's probably a half of 0 jobs arriving. On the other hand, if 2 jobs arrive, which also happens with probably a half, then the server can either work on jobs that are already in the queue or one of the newly arriving jobs. And at the end of the minute, a job will depart. But we had 2 that arrived at the beginning of the minute. So the net queue length at the end of the minute will actually go up by 1. So that's actually a simple symmetric random walk if you think about the movement of the queue when it has things in it. Of course, the queue can never go negative. And so if it empties out and there's not a new arrival at the beginning of the minute, the server will just idle, which actually makes a nonlinearity in the behavior of the queuing model. And of course, we can simulate this, and it's kind of fun to do that. So if you simulate, and on this axis, this vertical axis, put the number of jobs in the queue at the end of each minute, then you'll see that it can go up by 1 or down by 1. But if it gets to 0, then it can't go below that barrier, even if the server was able to work there. It just idles. So we get this up and down movement, but with this boundary constraint. And if you simulate for longer and longer periods of time, and it's a little bit like speeding up a movie if you look for a longer interval of time, and also maybe standing back a bit so that you can see the whole extent of the sample part, it starts to even look something almost continuous. And the other thing you notice about it is that it looks like there's an inherent scaling property that if you look at the amount of time here and the maximum height of the queue length or number of jobs processed, this height is about the square root of the amount of time you look at. And that this is a sort of time is like distance squared scaling that actually is endemic to this up and down movement of the balanced random walk. And in fact, there's a mathematical theorem that goes with this. This is not just something one can show with simulations, that if we take the queue length process and scale time by a large factor, say r squared, and divide space by r, so that's like, speeding up the movie and then scaling down the vertical axis so that we can see things appropriately, that renormalized queue length process actually converges in a sense of distribution to a new process which actually has continuous paths, which are called W tilde. It actually corresponds in this example I have to the limit of the waiting time that things have to wait in the queue. It converges to a one-dimensional continuous stochastic process, which is actually called a reflecting Brownian motion. And it has 2 pieces to it. It can be decomposed as a Brownian motion, which corresponds to the limit of those up and down simple symmetric random walks. So that would be the motion we have here away from the boundary, away from when the Q, for example, is 0. And then there's a process that only comes into play when the boundary is reached, when it corresponds to when the Q is empty. And this process increases just the minimal amount to keep this the sum of the Brownian motion and that non-negative, so that this W tilde will always be non-negative. And this process here is sometimes called a regulator. It's a continuous increasing process, but it only increases on this boundary here. So, for people who know control, this is a bit like singular control at the boundary to keep the process non-negative, just as Q lengths are non-negative. This boundary process here, in fact, corresponds to the limit of renormalized idle time for the server. This representation of reflecting Brownian motion goes back to Skorahide, and you may wonder about the name. It comes from the fact that this process is actually equivalent in distribution to the absolute value of the Brownian motion. Although it's better to actually think of it as maybe a regulated Brownian motion. Both of those you can think of as being RBM, which some people prefer to use. So this is a very nice process, but it has this nonlinear effect at the boundary. And in fact, you can write down an explicit expression in this one-dimensional case for that control process at the boundary. It's minus the minimum value you've seen of the Brownian motion up to the time t that you're looking at. So you can see that if you add this to the Brownian motion, it'll always be non-negative, and this process increases only when the Brownian motion reaches a new minimum. Here I'm starting the system from empty, which I'll do in all my examples. So this is a nice representation, but of course, this has been developed for some time now, and I considered a very simple example here, but you can extend the assumptions on the example I had to, you don't actually have to take things exactly balanced. You can take a sequence of systems that approach balance or heavy traffic and still get a approximation like this. It's just that the Brownian motion now will have a constant drift. If it's negative, then this will be a positive recurrent process, have a stationary distribution. You can use that to estimate measures of performance for the Q-length process. Also, I had a very specific scenario. There was a reliable server and the arrivals were just either 2 jobs or 0 jobs. But Brownian motion, it satisfies an invariance principle that you can have all kinds of random walks that converge to Brownian motion by this sort of rescaling. And so this approximation can actually be generalized where the inter-arrival times are independent identically distributed with a finite mean variance, and similarly for the service times. And the limiting process, its statistics will just depend on the first 2 moments of those inter-arrival and service times. So it's called an insensitivity property. It doesn't depend on the higher moments. So it's another thing you can glean from this kind of approximation. And this sort of approximation in terms of reflecting Brownian motion has a history through at least the 1960s and early 70s. Kingman did an approximation that's well known to the steady state distribution. Finite dimensional distributions of the stochastic process were done by people in the Russian school like Prohorov and Borovkov. The sample path version, which is basically the version that I've talked about here, is in the work of Eichelhardt and Witt. And just to illustrate the kind of thing you might be able to deduce from this, if you look at the average waiting time in the queue in steady state, so Kingman showed that you can actually write that approximately in this form in terms of various parameters in the system, but you can also glean this kind of result by using this approximation that has an approximation to the queues in a nilly balanced case. The parameters here are the arrival rate. 1 minus rho is a measure of distance from the balance point. Rho goes to 1 as you go to the balance point, and these parameters here tell you about the variability in the arrivals and the service time. So all of that helps to give some quantitative measures of how things like load on the system and variability in the system can affect things like waiting times and queue lengths. So this is a simple kind of warm-up example, but one thing you might take away from this is that what a difference a little randomness can make in arrivals or service, that one can actually get, even though one's balancing things on average, one can get substantial queuing types of behavior and analyze it using these reflecting Brownian motions, which are a reflecting diffusion process. So there's another aspect that I want to mention, and that is that often these resources are shared amongst different types of entities that are being processed in the system. So this is cartoonishly pictured here by a doctor who has to share his time amongst different types of patients. But you see this sort of sharing of resources also occurs even in applications in synthetic biology, where protein molecules compete for the attention of a shared enzymatic processor. And it occurs in other scenarios, for example, in internet models and so forth. So I'm going to illustrate what we might expect there with another simple example. And then, as I did before, I'll talk about generalizations of it. So now this is what's called a multi-class, actually still single server queue. So multi-class corresponds to the fact that now we have more than one type of job. I've colored those in yellow and blue, and they might have different arrival processes, for example, would be a way to distinguish them. And just to take a simple example, suppose that the arrivals to each of the queues are given by independent Poisson processes with average rates of lambda 1 and lambda 2. So that means that the inter-arrival times are independent, identically distributed exponential random variables. And then let's suppose also that the service times are independent and identically distributed with an exponential distribution. I'll take it to be the same for each type of job, with an average rate of mu for service, or a mean for those times of 1 over mu. Now, I'm very interested in these resource sharing situations where the resource is fairly shared amongst the different queues. So I'm going to still assume that when jobs come into a queue, they queue up in the order in which they arrived, and then the server is going to give service when it gives it to a queue to the job that's at the head of the line. That's called the head of the line service. But we still have to decide how the server will serve the different queues. And a way to do that fairly is to share the effort in proportion to how many jobs are in the queue. So in this scenario, the server would give 3/5 of its time to this queue and 2/5 to this queue. So that protocol is called head of the line proportional fair sharing. It can be implemented in practice in various ways, even by a round robin kind of mechanism. So we'd like to understand the behavior of the queue length processes in this model with now this fair sharing sort of protocol. And in particular, to understand how the queue length processes evolve with time. So now there's one queue length for each of the 2 types of jobs. And in fact, under the assumptions I've given here, these exponential and Poisson assumptions, you can analyze this model in steady state exactly. That was done by Frank Kelly in his seminal work on multi-class queuing networks, actually. So this is a special case of that. But so you can actually find the steady state exactly. It's in that case, the queue length process is a continuous time Markov chain. And you can, for example, compute the steady state correlation between the 2 queue lengths. So we're interested in the interaction between the 2 queues. So that's why I focused on this. Interestingly enough, this formula doesn't seem to have been written down before, even though you compute it from Frank Kelly's steady state distributions, until it came up in an application to synthetic biology that I was involved in a few years ago. But you can see here as the load on the system, which is given by this parameter rho here, it's the total arrival rate divided by the service rate. So when that's less than 1, the system is underloaded. The balanced situation is when rho equals 1. You can see as rho goes to 1, this correlation is going to go to 1. And that's just exemplified by this example here, where I've picked a particular lambda 2 and mu, and then lambda 1 can force you into that, going from the underloaded to the balanced regime. But it's not just in steady state that you can do this. If you simulate the sample paths, suitably normalized, divide by the arrival rate for each of the Qs. If you simulate the sample paths of the 2 Qs, you'll see that they're rather strongly coupled together when you're at the balance point, or even if you're near the balance point. So that suggests another mathematical theorem, which we can actually prove, that if we take our Q-length processes and do that same kind of diffusion scaling that I had earlier, time is like distance squared, then in fact you can approximate that 2-dimensional Q-length process by a constant vector, which is actually the vector of arrival rates here, times a 1-dimensional stochastic process, which actually turns out to be a 1-dimensional reflecting Brownian motion. It might be a constant multiple of the one I had previously, depending on what the variability parameters are, but it's still a 1-dimensional reflecting Brownian motion up to a scale factor. And so that allows us this sort of dimension reduction plus our ability to study these reflecting diffusion processes allows us to study this multi-class Q. And in fact, as before, one can actually consider nearly balanced systems. So when rho is near 1, and still approximate by this constant vector times a reflecting Brownian motion. Reflecting Brownian motion will have a constant drift now. And we can also generalize to where the interarrival times are non-exponential. So as long as they're IID with finite mean and variance, and for the service times provided here that they're they have the same mean for both all of the classes. So that's actually a special case of something that Bramson and I proved for networks of multi-class Qs with this head of the line fair sharing discipline. And so I want to just mention that briefly here. I'm not going to go into a lot of detail about it because I'm actually going to show you an example of this kind of work for stochastic processing networks, which is where I really want to eventually get to. So just as an example of one of these multi-class queuing networks, here's one with now 3 processing stations. Each one has its own little queue domain. The processing 1 and processor 2, they're actually single class networks. There's just one queue there. But processor 3 here is multi-class. There's 2 kinds of queues there associated with whether the jobs in the network came from processor 1 or processor 2. And now we have a new feature in these multi-class networks that there's routing in the network going from one station to another. In this example here, jobs when they finished at 1 go to this queue at 3, and then they'll actually depart after being processed at 3. Whereas at 2, they go here to this buffer, and then when they're processed at 3, they go through a probabilistic switch. So with probability, say P, they exit, but with probability 1 minus P, they're going to go back. And so in general, in these multi-class networks, you can have this kind of probabilistic routing where you can go from one station to another with a certain probability. So here also, there will be a dimension reduction at station 3, that things are actually there are just driven by a 1-dimensional process that's associated with the processor. Same thing for 1 and 2. And so you put those all together, what's driving the underlying stochasticity in the system is a three-dimensional process, which turns out to be a obliquely reflecting Brownian motion in the positive orthant of three-dimensional space. That's because Q lengths are always non-negative. So you have something here in the three-dimensional orthant. And there's constant vectors of reflection on each of the faces, but they're oblique. And let me just give you a hint at how these are formed. So when you're on the boundary of an orthant here, in terms of the reflecting Brownian motion, it corresponds to some process of being idle. So for example, if we here on this face here, it corresponds to processor 1 being idle. And so we'll do similar to what we did in the one-dimensional case in terms of behavior perpendicular to the boundary. You just keep it non-negative. But then also things from station 1 usually go to station 3. So there's lost potential flow to station 3. And so whenever you have some idleness to the server here, not only do you have a normal component perpendicular to the boundary, but you'll also have a negative component in the W1, in the W3 direction, that there's lost potential flow to that station. So that's a short explanation as to why you get this oblique reflection rather than normal reflection at the boundary. And that can lead to very interesting behavior, even questions about whether the process exists and is unique, and whether it hits edges of the orthant, that kind of thing. You know, Brownian motion doesn't hit points or even lines in 3 dimensions, but this reflecting Brownian motion can hit edges and perhaps even the corner of the orthant. So this theory that I already talked about for the 2Q example can be generalized to a multi-class QE network like this, with this fair sharing discipline that I talked about. And you get a sort of dimension reduction result where things are just driven by a process who has the dimension of the number of processes in the network or stations. And the reflecting Brownian motion has a nice decomposition now in multiple dimensions, where this R matrix has these vectors of reflection on the boundary in it. And again, here you have a process on the boundary. And now it'll be multidimensional. It'll correspond to effectively idleness of the servers in the system. So you get a nice process to describe these things. And one of the nice things I've liked about working on this theory over time is that it not only gives insights to stochastic networks, stochastic processing networks, but also leads to interesting questions for these pure mathematical questions for these reflecting Brownian motions. And so one of my students, Lisa Taylor, and I did early work on the existence and uniqueness of these reflecting Brownian motions, but there's been a whole host of work since on other versions of these reflecting Brownian motions and on their properties and so forth. In fact, a couple of weeks ago, we had a very nice workshop here at the Isaac Newton Institute on stochastic reflection and all of the marvelous developments that have occurred since then. So I won't go into how this state space collapse or dimension reduction and convergence to reflecting Brownian motion are proved here for multi-class queuing networks. What I would like to do is to talk about an example of this generalizing to stochastic processing networks. But before I do that, what are the things you perhaps should take away from this little discussion of these multi-class queuing networks? Well, one is that sharing of resources can lead to entrainment of stochastic processes like queue lengths that are coupled through a common server. And that can lead to dimension reduction in this heavy traffic or balance regime. And we can actually exploit that often to prove diffusion approximation for the queue length process, which through the dimension reduction reduces to study of that W process, which is usually called a workload process. So now we have this sort of theory for multi-class queuing networks that has been developed, although there are still outstanding questions there. And let me explain what I mean by multi-class queuing network. So you have these processes in the network, and then in a multi-class queuing network, they each have a little domain of buffers or queues that are processed at that server. So in particular, the mapping from queues to processes is many to one. Whereas in more general stochastic processing networks, as described in a beautiful paper of Michael Harrison, where he introduced this notion around 2000, you can generalize the connections between the buffers or queues and the processes in many ways, which correspond to interesting applications. So, for example, these are just examples. The structure is really quite general. A buffer might have the possibility that jobs from there could be processed by one server or another. So this corresponds to alternate routing possibilities in various types of networks, things like customer service situations where you might have cross-chain train agents or something like that. It's a quite flexible format. You can also have what I call simultaneous consumption. This occurs in input queued switches that you have in the internet, that when the processor processes jobs, it can process, in that instance, packets of data from more than one queue. This also occurs in manufacturing, where you have to take two kinds of items and join them together in a production mechanism. So this is also a scenario that transcends the conventional multi-class queuing network scenario. And another example is that perhaps to process jobs from a buffer, you need to simultaneously use capacity from more than one server or more than one processor. So this sort of scenario occurs, for example, when perhaps you take raw material and you send some of it in one direction and some of it in another direction, and maybe later on everything comes back together in one of these kind of joining type operations. So that I call simultaneous resource possession, and is actually an example that I'm going to use to illustrate some of the developments that we've been working on in that transcend what's been done for multi-class queuing networks, but can also lead to approximations by these reflecting diffusion processes. So I'm going to focus on this example for a moment to illustrate the kinds of things that we want to be able to do for stochastic processing networks in general. It's kind of like a test bed example to see whether our techniques can be generalized to this situation. So this was introduced around 2000 by Roberts and Massoulier. The idea is, think of this as a model for transmission of files through a data network, where files need to go through multiple links in the network. It might even be something like the internet. So in this, you have links that are like processing resources that have a fixed capacity, and you have routes, and a route is really just a subset of the links. So in this top picture, you have one route that goes through all the links, and then there's a route that goes through each of the links. Okay, think of that as maybe like something like local traffic or something. And you can have more complicated situations in a communication network or something like that. So this is actually an example of a stochastic processing network with simultaneous resource possession. And to illustrate that connection, let me just talk about that top example, the linear network, which I've pictured here, at least an example of it. So now there's three links, which are, think of them as resources, which with the finite capacity or rate at which they can transmit data through them. And there's three routes here that each of them goes through just one of the links. And then there's one route that goes through all of the links. And so files will arrive to each of the routes. and then be transmitted over the links that they need to go through. And you can think of this as a model with simultaneous resource possession, and I've redrawn it in this way just to emphasize that. So the routes that just go through one resource are pretty simple. They're like a standard kind of way you would draw something in a multi-class queue. But the route here that goes through all of the resources, it's going to simultaneously use the same capacity from each of the resources that it goes through. So if you think of, there's really like a reservation pipe that goes through these resources, and the same capacity gets taken out of each of them, even if the resources have different bandwidth capacity or rate at which they can transmit data through them. So we'd like to be able to understand this model. And so let's, like we did before, take a simple situation where we'd like to be able to understand it. Suppose that for each of the queues, which correspond to routes, there are Poisson arrivals of files at an average rate of lambda I for root I. Let's suppose that the file sizes are exponentially distributed with a mean of 1 over mu I for root I. Let's suppose interarrival times and file sizes are all mutually independent. Then it's sort of at the level of averages, the average load that is being posed by these files that come to root I is the rate at which the files arrive times their mean size. So this is the average bandwidth that you expect that route to require. Now, a distinction from most multi-class queuing scenarios is now the links, the processing resources here. Usually in a multi-class queuing network, they would have capacity 1, whereas now there's a capacity that can vary from link to link here, which is some positive number Cj for link J. So this model was something that Robinson and Soulier looked at. And now also, just like the multi-class queuing network scenario, I need to tell you how the resource capacity is going to be shared amongst each of these routes that go through the processing resources, through the links. And again, we'd like to do this in a fair way. So a natural generalization of what I talked about for multi-class queues is there's a policy called proportional fair sharing, which was introduced by Frank Kelly, associated with this internet type of modeling, which is a dynamic policy, just like the multi-class one was, that depends on how many files are currently on each of the routes. So if we form a queue length vector, which will have one component for each of the routes, where Qi is the number of files that are currently on route I, then the bandwidth allocated to route I, so allocated to Qi, is given as a vector by solving this optimization problem. The idea is that basically you want to maximize an overall social utility for the network, where the bandwidth allocation has a utility of log of the utility, that it's multiplied by the number of files that you currently have on the route, and then you sum over all the routes to get an overall utility for this allocation. The allocation needs to not exceed the capacity of each of the links, and of course needs to be non-negative. So one can solve this problem. It's not a very explicit solution, but this is a natural way to try and allocate the bandwidth. This proportional fair bandwidth sharing has various nice properties that make it a natural choice for a generalization of the fair sharing policy I described earlier. So now the question is, well, how does the queue length process behave when this network operates like this? And in fact, the first question is, well, what's the balance point? When is this network underloaded? When is it overloaded? So this was settled relatively quickly after the model was introduced. So if you have inequality here rather than equality for each of the links, so that's sort of the average load on each link is less than its capacity, then the network is stable, it's nice. And if you have one of these being violated, then it's something's overloaded. So the balance point is where you have equality at each of the links. The average load on each link is equal to its capacity. And so what we'd like to understand is how the system behaves at or near that balance point. And as before, under a mild rank assumption on the matrix that maps roots to links, in diffusion scale and with a sort of a measure of how much work is at each of the links, also in diffusion scale, one can prove a dimension reduction result that the Q links are actually driven by a lower dimensional, usually a lower dimensional process, which is a link level process. And that link level process can be approximated by a reflecting Brownian motion that lives in a polyhedral cone. Okay, so one of the interesting things about this approximation is that, remember when I talked about the approximation for multi-class queuing networks, the state space for the diffusion was the orthant. Now the state space is a polyhedral cone, which is strictly inside the orthant. And that geometrically represents the price that we're paying for using a fair policy where we have this more complicated network now where you have entrainment between different resources because you have routes that go through several resources at once, and there's a single bandwidth allocation that goes to that route through each of those resources. This reflecting Brownian motion has a nice decomposition as a Brownian motion plus boundary processes that again correspond to unused capacity of resources. And I know this is a little bit to get your mind around, so I'll show you an example of this in a moment, but it built on results that were developed over various parts of time in terms of getting the reflecting Brownian motions well defined and proving an invariance principle and eventually proving the convergence and making sure that the conditions were as relaxed as possible. So if I go back to the linear network, although the result I just described is general for those bandwidth sharing models, here there's 3 resources and 4 queues. So the first thing is there's a dimension reduction result called state space collapse. And unfortunately, I don't have time to go into the beautiful story associated about how you show that. That's a whole nother talk. But once you get that dimension reduction, you can focus on proving diffusion approximation for a process that has the dimension of the number of links. And that is a process that lives in a polyhedral cone, which is strictly inside the positive orthant. Here in this example, it would be in 3-dimensional space. The directions of reflection on the boundary are oblique. Since the cone is strictly inside the orthant, they're oblique even though the directions are parallel to the different axes. So they're parallel to the axis, which is represented by this just being R tilde, Y tilde. There's a no reflection matrix in front of it. But they're oblique because once the sides are slanted, then doing reflection parallel to the axes is an oblique direction relative to the normal to those faces. So we get this nice geometric picture that tells us. So what happens when you hit a face is it means that one of the resources is being underutilized in terms of its capacity. And so you get this sort of unused capacity process increasing. So we see geometrically what we're losing because of using a fair policy versus perhaps one that maximize the state space and minimize the unused capacity, but was not fair. And just to show you another example, which also leads to a three-dimensional reflective Brownian motion, so you don't think all the examples are linear networks. I do want to mention one more result related to this analysis, and that is you say, well, there's this reflecting Brownian motion, so what do you know about it? Well, it actually turns out that, so I mentioned before that you can consider a sequence of systems that approach the balance point where the limiting diffusion will have a drift. If that drift is negative, then it turns out that you can find an explicit formula for the stationary distribution for that reflecting Brownian motion. It turns out to be a nice exponential in terms of this drift parameter and also the various variance parameters that go into the model. And because of the dimension reduction that we have, that then gives a stationary distribution for the approximating Q-length process. I must admit that I did not expect when we embarked on this study of this bandwidth sharing model that this result would come up here. And in fact, Mike Harrison and I proved the underlying analysis of the stationary distributions, the so-called, satisfies the so-called skew symmetry condition back in the 1980s. And I think it's a testament to why it's good to work on problems just because they seem to be mathematically interesting, that they can turn out to have applications in unexpected places. So in fact, this skew symmetry condition comes up not only in this bandwidth sharing model, but also in atlas models in finance. Professor Ichiba, I think who might be here, can tell you all about that. So we have this bandwidth sharing model with these Poisson assumptions and exponential file sizes and this proportional fair sharing policy that we can analyze in terms of a reflecting Brownian motion. Let me talk about some other problems just related to this bandwidth sharing model. In fact, the proportional fair sharing is one of a family of bandwidth sharing models, policies that one could use. There's actually a family that was introduced by Mo and Mulrand, and the one I talked about corresponds to alpha equals 1, where we have an analysis. If alpha is not equal to 1, you can still allocate policies, and some of these are especially interesting, like alpha equals 2 corresponds to TCP protocol on the internet. The state space collapse, the dimension reduction has already been proved for this family of policies. What's still open, at least in some cases, is to prove the diffusion approximation for the W tilde process that I mentioned earlier. And let me show you what the issue is. If alpha is bigger than 1, the conjectured diffusion state space is a cone, but it's no longer a polyhedral cone. It has curved boundaries. You can see an example of a cross section here. And there's very recent work of Cristina Costantini that shows, at least in some circumstances, this is a well-defined diffusion process. It's still to be done to actually prove that the bandwidth sharing model converges to this diffusion process. But this is very nice recent progress on the underlying fundamental theory for the diffusion process. When alpha is less than 1, it's a little bit more tricky because the boundaries are again curved, still a cone, but they meet in cusp-like singularities. And there it looks like maybe one has to go dimension by dimension. There's some nice recent work of Costantini and Kurtz addressing that issue in 3 dimensions, but higher dimensions is still a challenge, and actually proving convergence to the diffusion for the bandwidth sharing model is open. With this bandwidth sharing model, I talked about the exponential and Poisson assumptions. It's natural to try and generalize those, and that's actually been done when you do head of the line service. That is where files queue up in the order in which they arrive. However, in fact, the bandwidth sharing model really the bandwidth is being shared equally amongst all of the files on a route. And so that's more like a processor sharing kind of discipline, which would be a non-head of the line discipline, which is work on those kind of models there's still a lot to be done. There's been some done for a single processor sharing queue with the bandwidth sharing with Poisson arrivals and certain types of file sizes, those with phase type stability has been analyzed, and also stationary distributions. But with general distributions and inter-arrival times and file sizes, stability now has been found that the stability condition or the balance condition is the same as what I described when you have Poisson arrivals and exponential file sizes. And very recently, with Ying-Jia Fu, we developed a precursor to the state space collapse. So I think we're getting very close to being able to do the diffusion approximations with general inter-arrival times and file sizes. So this bandwidth sharing model, as I said, it's sort of the quintessential example to sort of as a test bed to see how our techniques work for trying to approximate these stochastic processing networks, and including with non-headed aligned disciplines. There's still a lot more that can be done, and I think that's where there's some very interesting open problems which generate new mathematical questions for these reflecting diffusion processes. Let me sum up by just trying to give you a little bit of perspective where I think things stand. In this column, I have multi-class queuing networks. In this column, the more general stochastic processing networks. Across this way is those with head-of-the-line service, which I've talked about a lot here. And here is non-head-of-the-line service. So for multi-class queuing networks with head-of-the-line service, we have quite some good techniques there, and a lot is known. There are still some open questions. For more general stochastic processing networks, stability has been studied with phase type distributions, but more general distributions, there's still more that can be done. And for diffusion approximations, it tends to have only been so far for things that were motivated by particular applications. I talk here about the bandwidth sharing model with exponential file sizes. For more general multi-class queuing networks with non-head-aligned service, there's still a lot to be done in terms of networks. There's been quite a lot on specific disciplines for a single station or some feed-forward networks. And this box here is like the Wild West, that to try and do general stochastic processing networks with non-headed aligned service, there's a lot of things to be done. We're starting to make some progress, I feel, with these bandwidth sharing models with general file sizes, but there's still a lot more exciting things to be done. And I'd like to thank you for your attention and acknowledge very much this opportunity to give this talk. And here's a picture of the few of my collaborators that I mentioned here. So thank you very much.
Thank you very much, Ruth, for this very nice overview lecture of stochastic processing. We have 38 seconds for a question or two, if they're short. Go ahead, Chris. It's okay, they're picking up the mics. Okay. Speak up.
So hopefully it's a short question and short answer. It seems to me that all limit processes that you mentioned were variations of Brownian motion, or perhaps more generally, but they seem to be all continuous. Are there any cases when in the limit you get jumps or discontinuities?
Yes, people have looked at. So as I said, I took a very special slice of what's been done. So if you have, say, arrivals or service times that say IID but have heavy tails, then you can get, rather than convergence to Brownian motion, you can get convergence to things like a stable process or something like that. So Ward Witt, for example, has a very nice book that would be a place to start to read about that kind of thing. Does that answer your question?
Yes, yes, thank you. No other questions? let's thank Ruth again for this nice.